7.
Okay, so in the last lecture we have found this a very nice and compact formula for the n open superstring amplitude. Let me just write it again. So we had some vector of describing open superstring n point amplitude. Pi is a n minus 3 permutation, and this was given in terms of a matrix multiplication in the following way. Where this was this fundamental worldsheet integrals, and then we had some other matrix, and then the so-called super Young-Mills vector, where all space-time kinematics enters, while here all string effects enter. So this is this real string worldsheet is integral, while this it's really super Young-Mills. And then what we will do this afternoon is we will see that for the gravitational amplitude in field theory, so we scatter gravitons in supergravity, we have an amplitude which n-point amplitude which looks as follows. So strictly speaking, this is the Young-Mills amplitude. I mean the amplitude describing open string endpoint scattering. There will be also a coupling, which is the Young-Mills coupling. And remember, yesterday I told you that the Young-Mills coupling is related to e to the phi, which is the string coupling in type 1 superstrings in phi secular term. So we have precisely the same form of matrix multiplication, only now with one of these C's, I mean the worldsheet disk integral exchanged with the Young-Mills, with another Young-Mills sector, other Young-Mills factor, because we know that for gravity, to describe gravity, we have essentially the double amount of polarizations to get two vectors. So we will derive this formula in a very cheap way from considering closed string amplitudes later. And then we take the alpha prime to 0 limit, and then we get it actually. And this is really nice that we have this corresponding. This is a very nice formula. But before doing this, I want to discuss the high energy limit of these amplitudes, because this is very much related to recent developments by Schwarz et al. On describing super Young-Mills amplitudes and scattering equations. So recall that we have from this formula in particular we get the 4-point superstring amplitude, which we have worked out. So there's 4-point Young-Mills factor and a form factor, and this form factor is was this ratio of gamma functions. And S and U are kinematic invariant or one-dimensional variables. What we want to do now, or what we want to investigate now, is how does this amplitude behave when alpha prime goes to infinity. So this is a completely opposite limit as, of course, really sending alpha prime to 0. So we now alpha prime sending to 0 gives just reduce field theory, which you clearly see here. When I send alpha prime to 0, that is two guys go to 0, so then I'm just gamma of 1. Now and then you see this factor becomes 1, and then I have just the opposite. Recover while the alpha prime goes to infinite limit is the so-called half scattering limit. So this essentially means that S and U become go to infinite. But clearly, while all Mandelstamm, before I mentioned here, there are also certain Mandelstamm are T, and so this is just plus T equals to 0. So when I say this, all three Mandelstamms go to infinite, of course, this can only happen if one of them is negative, and this is actually for a real physical scattering process in cases. So you can parameterize this Mandelstamms or just with true scattering parameters, which is the energy at rest and the scattering angle between the first and the third quantity. So with this you first see that S is really negative, and second you see that this is This is just to convince you that S has to be negative. So how do we do this limit, or how do we compute this limit? I mean, it's not so difficult if you know how to do a subgroup point approximation, or more precisely what the Laplace method is. So let's write this f to the 4. Because here we don't have to do anything because this doesn't depend on alpha prime, so it just stays. So let's first rewrite S and this factor here in the following way. So this is actually precisely how we got it. So this is a trivial rewriting. I mean, I just call this stuff without the alpha prime is the hard quantities. This is simply because then I see better what now I see better what I have to do, or where alpha prime goes to infinite enters. And now let's. So this is clear, and this is just when you just gives me Euler beta factor here, and I just use the gamma 1 plus x is x times gamma 1 x this factor here. Now this is nothing else than, I mean, I just write it in terms of exponential. And for this object, I can use the so-called Laplace method to approximate the integral for alpha prime goes to infinite.
So where does the x to the power minus 1 come from?
What? The 1 minus x?
No, that one. Yeah.
This one. Because it should be here. Yeah, I forgot to write it here. Sorry. Thank you. I mean, now it gives. This gives when I integrate it, alpha prime is up. Plus 1, and then times s. So then, what is the Laplace method? The Laplace method can be used to approximate an integral which has in one variable which is precisely this formal. So let's write this down. And there's some of the conditions we need that this function has a global maximum. It must be unique. And the maximum must be in the integration. That means, of course, the first thing is we have to compute the maximum, and then what we need to do with the maximum is the following. This is what the Laplace method tells us, or the multi-dimensional case is called subtle-point approximation or method of Stieberger's descent. That is what we need to apply then for the general end. So, I mean, this Laplace method now continues here. So now we have to do the following. So, given such an integral with f fulfilling these conditions, then this can be approximated by this expression. And this will give subnating terms. And you have to evaluate the function with this exponential and maximum. So for the present case, for the present integral, it means okay, our integral is s hat ln x plus u hat ln 1 minus x.
Could you make it short, please?
And then okay, the first derivative is s hat. And so from here I get the maximum, which is 1 over t. Of course, here I use the relation between x plus t plus u, which clearly holds also in the half quantities. And then I need this object, second derivative, which can compute to be this. And I'm creating f of x, which can be converted to here. Now you can get an approximation for the f4. So the f4 is for alpha prime goes to infinite minus alpha prime s. But now I will write to quantify it. So times and then according to this we get subleading terms. So this is the high energy limit of the four-point amplitude. This was also now just to warm up for the endpoint case. So or are there any questions so far?
This goes to infinite with alpha goes to 0. Well, if alpha prime goes to infinite, this function also goes to infinite.
No, because what happens I think it's correct, but let's just verify. So that is what I get with the hard quantities. To the 3. So this is clearly well, this is what I got. Alpha prime 0. And this gives S hot, T hot, and the alpha prime I can put in the square alpha prime in the square rule, and then I can convert it to S. And so this is the correct formula. You should remember that here the alpha prime is not drops out because writing, first of all, so whether I write alpha prime, the alpha prime in the logs it drops out because you can write each log as hard alpha prime. And times S plus log plus U log and so on, and then you can just get the alpha prime, and so you get S plus T plus U log alpha prime. So it doesn't matter whether you write here S or S hard because the alpha prime drops out. And then here you have, here you have alpha prime now. Which has to be there because S is a dimension full quantity, so the alpha prime has to cancel the dimension to make it dimensionless, the exponential. So this is all correct. This is the leading term, and then sub-leading term also depends on alpha prime, but it's of course smaller. So for the endpoint case, now we have to worry about how do we do this such a subtle point approximation for this generic disk integrals, which depend on, after fixing the matrix operator positions, depends on n minus 3 variables still, and for that we need subtle point approximation. So we have for the endpoint case. To the subtle point approximation on this expression. And for this we need to apply some subtle point approximation for multi-dimensional integrals, which is the method of steepest descent. Let me just explain to you. Sample point. And this will then from there we will get this so-called scattering equations. So again, generally we have an integral over the Rn of some function. Das sind dann vom Orderparameter Alpha auf Alpha prime. Then f needs to have isolated saddle points, so you should not have multi-saddle points. Points which have some degeneracy, degenerate extrema. So you have to compute them. You have to know the base case and they are in this region. These are determined, of course, by this equation. The second derivative should be not zero. Now, if this holds up, then we can, like in the one-dimensional case, we can approximate this multi-dimensional integral. In the following way, now we get a sum over all saddle points, which fulfill these equations. Let's denote all by the index point. For a concrete example here, it means that our function here is this function depending on the unfixed positions. So we write it in terms of exponential, and again we will use this S hat quantity to factorize the alpha primer.
Sorry, this is fine. So this is all real. So I'm not sure I understand why do you consider only saddle points. I mean, the function might have a maximum. Does this work for maxima, or does it work only for maxima, or really for saddle points?
These are saddle points.
Okay, so you don't need to choose a path through the saddle, or
no, you have to choose. This is of course the main point, that you need to choose a path from you. I mean, let's say here you integrate in R2. Maybe you integrate from here to here. That was your original integration I. And now let's say you have found your maximum here and here. What you have to do now is you have to deform this integration by Cauchy's theorem and go through this path. The main point is that you have to end.
so this is valid if all the functions are analytic. So this is actually a complex theory.
Well, you can have R2 and
yeah, but I mean the theorem that allows you to deform is valid for analytic functions.
yeah, but you can write it as a complex function and then you
Okay.
just take two variables.
Yeah, I was just asking. So we're assuming that that this has some analytic continuation, so there are no poles in these functions, etc.
Yeah, okay. You need to assume that you can find such.
Also because then this implies that the only thing you can have is actually saddle points. Otherwise, the function could have also global maximum.
Right. Mm-hmm. No, that's why you need to collect or determine the saddle points.
Okay.
And this is of course precisely what we have to do also here, because this is some path and determine some path in the Rn minus 3 and the saddle points might of course be complex. I mean, it was only an accident in the 4-dimensional cases, the saddle point was real, and then we have to collect them in the complex plane, collect all the saddle points.
Thank you.
So now, how do we determine these equations? I mean, the saddle points. Well, we have to differentiate with respect to all our variables. So we get a priori n such equations. So these are the equations to be solved to determine the saddle points. And this equation you might have met in different places. This is a scattering equation. So now are scattering equations. Are there still questions or?
I think not well formulated anyway. Not well formulated yet.
Yeah, we can discuss further afterwards. So these are the scattering equations, so you have to solve them. And of course, the simplest case was what we discussed before for foresights. We know that we have that there's a PSO2 R symmetry on for this open string disk integrals, which allows us to fix 3 of these vertex operator positions, and then actually the equations boil down to one equation only, which is precisely the equation we had before in the 4-point case. So this equation has PSO2 R symmetry. So we can fix 3 positions. And you can show that that these equations have n-3 factorial solutions. That means n-3 factorial saddle points, which is of course just 1 for 4-point scattering. So now we can apply this formula, and for this concrete case, we have already determined the saddle points here. I mean, the only thing what we want to do now is to write this determinant in terms of the quantities from before. So we have to compute the Jacobian. So let's introduce this function. This is just Jacobian of this function we are which subsequence we are determining. And so this matrix is SLT SLC squared. And then this, using this formula, you get finally a sum over all n minus 3 factorial subpoints. This is Jacobian. And which the prime means that you only need only allowed to take the unfixed matrix operator positions, and then we insert the subsequence here. So let's call the subpoint or denote the subpoints by chain. So I have told you already that this set of equation also appears in the context of describing super Young-Mills theory on in a very neat form by Kaczarczyk et al. And so you see there's a striking connection between the high energy limit of string theory and somehow the field theory limit of string theory, and the alpha prime goes to zero limit. And
so, is there a deeper reason why you get the same? I mean, you get these scattering equations, which are the.
There's not yet known a deeper reason of. I mean, there was. I mean, there's not known. I mean, this is a learning question how you can relate. Or I mean, so you have a perturbative string amplitude, and so its low energy limit describes Young-Mills, and its high energy limit is also related to Young-Mills. So it's not clear.
So if I remember correctly, the scattering equations are in field theory are associated with some nice geometric picture that they describe it. So does this picture have some naturally arises from string theory?
No, not yet. I mean, there's but there's one very nice aspect which I don't want to go into detail here is, but you can even do it as a homework. That is, if you now go back to this open superstring amplitude I showed you before, so this is just take the canonical ordering for the superstring amplitude. It was the sum over n minus 3 factorial permutation of the Young-Mills amplitude, and then just kernel. and then the C. So let's use one. Now, if you now plug in, so now we have computed the subtle point for one of these functions here, but actually they are appearing in -3 factorial. So you would expect that now you get a double sum over this. You get that you get not only that you get a double sum over n-3 factorial. I mean, for each of this function, one sum over n-3 factorial subtle points. And now you take this formula by Casciazzo, that you can also express this Young-Mills amplitude as a sum over the subtle points. So you get two double sums over subtle points. And recall, I mean, the subtle points describe something completely different. Here they describe subtle points in string world, divided in the Casciazzo case. They describe subtle points on this complex plane, describing the Young-Mills solutions. And then there's the so-called KLT relation holding between subtle points. That is, if you, I can just write it down. No? So then you will see again this mysterious appearance of this so-called KLT kernel, which tells us that you have only that the sum of the subtle points. So you have the sum one set of subtle points is denoted by I, and the other one is denoted by J, and then you have this kernel. So you have from here you have this from the string expression by plugging into here. So you have well, this is the sum from each of the virtual string integrals. So you have C1, up to N1. And the super Young-Mills amplitudes, they are expressed as a sum over subtle points in twistor space with sigma N1, and these are the subtle points denoted by I. And so this is now a very complicated double sum over subtle points you will get from here, and in addition, we have also this sum to describe the string amplitude. However, as Casciazzo et al. Have shown, this is the only. I mean, this is just a chronicle. And this is really a mystery. Sorry, I forgot to say that these sigmas, they act on this position, so they really go into this row, respective in this ordering from this Young-Mills. So this is just a canonical case. So the sigmas act on this position while the row acts on here. So you sum over all these commutations, and which is also here, and then you get delta IJ. Sorry, then this is the sum you have to do. So do the sum for one subtle point J in this on the string world sheet, and for another set of subtle points from the Young-Mills set, and then you get the chronicle. So by that you can imagine that when you write down the high-energy limit of this open string amplitude, that this formula highly boils down to something very compact.
So in some sense, so the fact that the same scattering equation appear on both sides, like if alpha prime goes to infinity and alpha prime goes to 0, is somewhat the same kind of problem the same kind of mystery that makes Z and A having the same symmetries. Like n-3 basis, it's also
to some extent it's directly related. Because you see here that the Young-Mills amplitude somehow has the same writing as the string virtual diagrams. So this correct formula I don't want to show you. So the correct formula for the full open string high energy limit, because I didn't want actually to go into details of this. So for that you need to to insert here the subtle point sums, and then you also have to express this Young-Mills amplitudes in terms of this Cacciazzo formula, Twistor space, and then use this KLT orthogonality relation, and then you get something nice. But this you can read in my recent paper with Swali et al. Then there's this formula shown. And actually there it's also described in more detail what you have to do when, because the subtle points, you do a real integration, but the subtle points might lie in the complex plane, what you have to do. This is.
Does something else interesting come out if you take a Regge limit instead of a Hart-scattering limit?
Whether something interesting comes out if it takes a, you mean the Regge limit or the Hart-scattering limit?
Yeah, instead of the Hart-scattering limit, some other limit in there.
No, the Regge limit is the limit where not all of the Mandelstaams go to infinite, but just the subpart. I didn't find it so. I don't find it so interesting. Because then essentially you have not the full set of scattering equations.
Okay, so you get just a
because
sub information.
Yeah, you get somehow a subset of scattering equation, and so you don't find this link to the super Young-Mills. I mean, let's say the problem for both limits is that you cannot solve this equation beyond 6 point. So this is therefore it's you can actually only write something nice which looks nice formally, but doesn't. Yeah, it certainly requires more research, especially about this connection alpha prime goes to infinite versus alpha prime goes to 0. And for example, to find, a string theory which reproduces the Cacciazzo, I mean the scattering equation for field theory in the alpha prime goes to 0 limit. This would be a one task. Are there any further questions?
So just to be sure that I get the main point. So this strong similarity between alpha prime equal to 0 and alpha prime equal to phi has been investigated for spin 1 scattering amplitude. Am I right? So for Young-Mills and the field theory.
You mean what I did here?
Yes.
This is for yeah, this is now for spin 1. Yes.
And so this generalizes to other amplitudes? Because I mean, it could be that this is special of spin 1, but
yeah,
maybe
okay. Now we move on to closed string, which is spin 2.
Okay.
And on Friday we see how this all is related. So to make it short, considering the high initial limit of spin 2 is qualitatively just the same.
As the multi-graviton.
As a multi-gluon.
Okay.
Multi-graviton high energy limit is qualitatively identical to multi-gluon.
In the alpha, okay, so for on the closed string side, this for alpha prime to infinity and for alpha prime to 0 is the same because you get the.
No, for alpha prime goes to 0, of course, you in one case you should get super Young-Mills, in other case gravity, the formula I wrote down here. But I mean, if you we'll find some projection which tells you that there's a much deeper connection between closed superstring graviton amplitudes and superstring gluon amplitudes, from which, for example, you can immediately get you take the high energy limit of the open string amplitude and you get it by free the high energy limit for the closed string amplitude. You do not really have to do a new computation.
Can I ask, here you're computing the higher energy limit alpha prime to infinity for the Zn, which is the basis of integrals.
Yes.
So this one described the hard scattering also for of massive string states, because any amplitude you can.
Yes, the only difference is,
yeah.
if you remember, it was there was this S factor, and which then was this 1 over x in the integral, and so for other states, like massive guys, you might have different polynomials. So it's subleading pieces which, which will be different. But this exponential is the same for any massive.
Whereas the relation between alpha prime to infinity, alpha prime to 0 holds only for the Young-Mills, because then you don't have scattering equations for massive states.
Because so far Kashatze and I have only done this, but actually there will be a paper out tomorrow or in 2 days by Young-Mills, which will be more general.
Yeah, but okay, they cannot do higher spin, massive higher spin.
Yeah, I will
scattering.
But I think they want to do also with massive, at least. And, so I think they also believes that this concept of scattering equation
holds also for more general.
I mean, they have recently there was a paper by them extending the scattering equation by Young-Mills to Einstein-Young-Mills, which is mixed amplitudes with gravitons and gluons. And now I think tomorrow on the day after they will have one of the multi-traces. Further question or?
No, just a small comment that this is strange because alpha n going to 0, alpha n going to infinity with respect to the massive states, I mean the high spin states it's very different. And if alpha n going to infinity, you might expect to have some kind of symmetry appearing in the scattering.
I mean, I do not know more on higher spins. I don't know. I mean, so I mean, I would compute this amplitudes involving massive string state, and then I mean, you could take the alpha prime goes to infinite limit. It should be similar as here because you write everything in terms of your basic building blocks, and then what the result is supposed to mean, I don't know. But I think it should be a well-defined task to compute it. I mean, of course, in this limit, all your heavy string, or supposedly the heavy string modes become all light. So, I mean, I don't know what it means when you single out just one massive state and scatter it, and do not include all other higher levels. So, this might be different, but I don't know. I mean, I have not done the computation. So now let's move on to the closed string amplitudes. So closed strings, as you know from your starting string theory, describe gravitons in particular. I mean, massless closed strings are gravitons. And now actually, to warm up, let's just make an example first. Namely, we consider four graviton scattering. I mean, of course, you have the knowledge that this might be the same in type 1 or type 2A or B. Superstring theory. I mean, they have the same massless. I mean, they all have a graviton. So what we want to compute now, so we have learned how to compute, or at least how to set up the computation. Now this is the basics what we did at the end of the first course. So we have now a closed string amplitude. So we have all 6 real filling vectors. I mean 3 on holomorphic and anthropomorphic side. And then we need graviton vertex operators. So they have essentially a product of a left and right moving clone vertex operator. So the graviton vertex operator is nothing else than a product of two H vertex operators, and this is one reason we should expect some essentially that the amplitude will be some square of H amplitudes. Strictly speaking, this is you should replace alpha prime with alpha prime over 4 when you do this. Then you can apply all formulas, which for example means that when you have this Cooper-Nielsen factor, okay, we will come to this anyhow. So now we are on the sphere, and on the sphere we do not have interactions between left and right movers, so we can completely separate, since we see that the vertex operator is a product of left and right movers, we completely separate the computation to left and right movers independently. So that means the first observation is that this computation can be done as follows. So we have the integral, which is the same as before, but we have two, and taking the splitting, we will have two correlators of 4 clones to compute or to insert. So one from anti-holomorphic part. And the same was from the holomorphic part. And actually we know what that boiled down, because we did already the full-fledged, or we know the result of the full-fledged open superstring amplitude. So we know, except of the integral, we know what this has to be. This was also what we have seen just before. Of course, now we do the fixing. We fix 3 vertex operator position. The first one is 0, and the same for the anti-holomorphic positions. And the second one will be integrated over, so the anti-holomorphic. And the third one is at 1. And the fourth one at infinite. And then this we know how we can reduce this. We know that we get this times, yeah, so that's kind of clear. Yeah, I want to actually want to write it. So I want to write the holomorphic and anti-holomorphic pieces below. So we know that we get this times S and times S. 1, 2, 3, 4. And another young mass amplitude 1. These are the objects which encode all kinematic factors, and which comprise into a graviton zeta. Just like here, here we have a clone polarization from one side and from the other side. Sometimes there will be written as a tilde and here is the psi, and then these two go together to form a graviton state. Similar here, so I could now also put a tilde simply. So is it clear that we get this form? We know you should have in your notes that when we did the superstring computation, we got something like x times the super young Mills amplitude, right? This was the object. That's a small name, and then we put things together and got this gamma factor times the young Mills amplitude. And the S here was this kind of KLT kernel. So, and now we do such this manipulation on both sides because we are coupled, both correlators. We get this and we get that, and except we replace x with c and vice versa. And of course, we cannot yet integrate it because here we have a real integral. Now we have an integral on the complex plane. So now this is exactly what we have to understand now, how to continue from there. Is it, I mean, all other questions? While we have this for the graviton case or closed string case. And we just do the same what we did for open string, we do now on both sides. And that's this. And so, I mean, we can now write it in put things together, or let's make a new equation. So this M4, this is 4 graviton amplitude, is now S squared, and we will just put things together. And in this 2 units, factors push. And then times this complex integral. S minus 2 and 1 minus u. So we have to understand how to do this complex integral, right? This is what will be done after the break, I guess, and it will lead us to the so-called KLT relations. But let's, for the moment, let me just give you the result for this. I mean, we already derived it, but let me give you the result for this integral. So S, T, and U are the answer, which I have written now before, and S plus T plus U is 0. So, assuming that this is the result of this integral, let's rewrite this formula. So let's do 2 steps, 2 very easy computations. So what is S squared times this integral, which we define this integral I, which is this expression. There's also I missing. So S squared times this integral is you can do as homework. It's sine pi s gamma s plus 1 gamma 1 plus u gamma 1 plus s plus u times another ratio s okay, 1 plus s 1 plus t S plus t times u over 2. I mean, this is a trivial computation. The only thing what I have used is that gamma of x times gamma of minus x is pi over sine pi x. And now I use another, so this is the first relation I'm using to rewrite this garbage formula. And the second one is that I use something what we have learned yesterday about these amplitude relations. So I can express this amplitude in terms of a basis of one amplitude, which is the canonical basis, and so basically you can just look in your notes and see that this amplitude in the field series, so it's field theory amplitude, so there are no sine factors, is u over t. So that means you see already here, there's this guy and there's this guy. So now we can. So now there's one thing we can see already. Remember, what is the open superstring amplitude? In the canonical ordering is this Young-Mills factor per times this factor, right? And so we can, after putting things together, we can write. So we can write this is amplitude. So we have the sine factor here. And we have one open superstring amplitude, full is 1, 2, 3, 4. So this is this color. And now we have another superstring amplitude which is 1, 2, 4, 3. Where does it come from? We have already seen that writing this tilde in terms of this gives us a factor t over u, which cancels this factor. So this amplitude will then be 1, 2, 4, 3. But of course, in order to describe the superstring amplitude with 4, 3, also the form factor has to have the Langmuir form. So what changes from here to here? We only exchange 3 and 4, which means S stays invariant while t and u are exchanged. So exchange here t and u to get this expression here. So it's precisely superstring amplitude. This is canonical. This is ordering. And I mean, to be precise, these are now the open string amplitudes which involve the Young-Mills squared coupling. So we should really also now write. I mean, you don't really need to care about it. So this open string coupling cancels the Young-Mills coupling, and then here we by hand put the closed string coupling to get the gravitational coupling. So yeah, in other words, actually this is gravitational coupling square. So now this is already quite nice because it precisely fits in the formula or in the pattern we have seen for the gravitational amplitude. So now you can. So this is the full superstring closed string amplitude. So it's a gravitational superstring amplitude. Now you can ask what is the field theory supergravity amplitude. So we take this formula and take alpha prime goes to 0. Then of course these guys become Young-Mills amplitudes. I mean this is what we have learned in the morning, and then here the S contains this alpha prime, so we just expand it. So so we get S. So sin S time pi S expanded. This is for alpha prime, this is just S. And then we have this Young-Mills factor, so we have this expression. And when you look in your notes from this morning, this is precisely the form I gave you. It's also the form I wrote down at the beginning of today's lecture, which was a double sum describing anti-gravity on amplitude. So you see the trivial 4-point case is given by this, and this again, sorry, this formula I gave you at the beginning of today's of the lecture. This is the kernel, again the kernel. Interlining between two young millisectors. Of course, for the 4-point case, it's just a scalar. So this was a scalar which we have already seen a couple of times. So this for 4-point precisely gives the formula we have seen already. And so in the next, after the break, we want to derive this complex integral and then also get the triviality. Shall I make a break or?
Yeah, you should.
Okay, so now I have promised you that we want to understand how to build such complex integrals, because they will then lead us to the famous KLT relation. So, so this was a complex integral we had met, which corresponds to this fixing of closed matrix operator positions. And actually, I consider now more general. So we have these Mandelstamm's, which are real numbers, and we have this integers n and so let's just so let's try to do this integral. So if we split this complex coordinate C with real and imaginary part, then let's just look what we have to do in this respect to x and y. Clearly, x and y in this have to go from minus infinite to plus infinite. So now let's go into the complex y plane, and clearly the y has to be integrated along this real axis. Let's call it C1. And then similar for x. And so when you write this polynomials in terms of x and y, I mean this is of course trivial. I mean they look like here. So for example, when you are in a real y line and y axis, this has a 0 at plus minus ix. I mean at minus ix, and then here for plus ix. In other words, you have zeros along the imaginary axis. I mean, while it now it has the x is bigger or smaller than y, and it's just assume it's like that, doesn't really matter. So okay, so this is a case just for the moment, let's assume this. And as I said, this is a complex y plane, and so there's no problem when you integrate from here to here, because this y integration does not have any branch points, because all branch points are along the imaginary axis. So there's not a problem we had yesterday that we had to worry about how to make this integral well defined. But we will now soon have this problem because we want to deform this integration here. So we want to deform it to this counter. So what we do is we want now to integrate along C2. And of course, again, there's nothing to worry about when we deform this to infinite, this circle, because we have this conformal fields which behave, which are conformal with weight 1, and so we have they behave all with powers of c to the minus 2. So now let's write down what we have. I mean, let's first parameterize the integral now with this new coordinate. So we have a new coordinate y tilde, which is y, and now this new coordinate goes from minus infinite to plus infinite. And what we can do now is we can first of all write our x, our c coordinate, which was here, of course, y tilde, and this is c bars. This. Let's define this to be new coordinates, psi and eta. And okay, I mean, let's just, then we have done it. I mean, we don't, but it's, we see, or it's already obvious that we do some coordinate transformation. So let's just compute the Jacobian. Then we have done it already, we don't have to worry anymore. It's just fluid. So the Jacobian of this coordinate transformation, so the two-dimensional problem, is so, and of course, when you replace this, I mean, this is of course ideal. So what we get here now, if we do this change of variables, so this integral turns into this is -2 I over 2, so the I comes from here, the 2 comes from inverting. So since x and y both, since x and y tilde are both from minus infinite to plus infinite, so this nothing will change with integration relation. So both are still integrated from minus infinite to plus infinite. And then, so this is, so the c, we have now learned, I mean, it just becomes the psi, I mean, becomes a real coordinate. And so the c becomes psi, and the c bar becomes eta. Okay. So far, everything is was just trivial manipulation. But now we are in the same problem. It's the same problem as yesterday, that we have written down an integral over a function which has branch points and which does not make sense. So we have to make it. We have to worry how to make the integral single valued and how to get a meaningful integral here. So we have to, again, like yesterday, we must choose the correct branch of the integrand such that this is well defined. So write down what we have to do now. We must this example is the same problem we had yesterday when we did this analytic continuation in the open string positions. I mean, clearly we should not get branch. We should not get any trouble from branch cuts, because here we have started with an expression which doesn't have, which is well defined. So the potential branch points came from C goes to 0, for example, or C around 0, but since we have holomorphic and anti-holomorphic pieces here, there's no monotropy, and no matter how the integers are. So the problem comes only if S and U are from the S and the U's, because these are real numbers which produce the branch points or branch cuts. So it doesn't matter what the ends are at the end, because they will produce the branch points. So we have to render this integral well defined, so we have to choose some phases to get rid of the branch cuts. You can first investigate the branch cuts and indicated a guess is that one should introduce the following phases. And this is very much in line with what we did yesterday. So this zeta is essentially the same quantity I defined yesterday. Now this quantity does the following. It's either 0 or S. It's the product of these two variables, are bigger or smaller than 0. So with this phase, our integral becomes well defined. So that is what we have to introduce here or multiply this integral. And of course, then make everywhere absolute values here. Then we have a function without branches. Now this integral I now becomes I over 2. So that is, we are now put this absolute values everywhere, and by this we get rid of the branch points. And have what is this space instead. So you see that this integer part doesn't play any role in the discussion. So we will get full-fledged the full-fledged generic result by independently on what we are doing with. Or what these integers are, and then you need to use the space now. So of course now this might look very complicated, this phase we have introduced here, and so let's see how we can better understand this phase. So how can it be described? So what we will do now is that we want to get rid of this phase by changing these integrations. So in other words, we want to we will go now into the we will again now consider complex eta. Also, this is a real integral, but so we will go in the eta plane and see by deforming this integration along the real line by introducing some counters, which will will precisely describe these phases, then we can get a much simpler form. So, what does it mean? What we will do now?
Sorry, I missed completely. How did you choose the branch here? Because here there is, I mean, the fact that you choose 0 and less and not something like plus 2 pi I plus some integer on theta, it's exactly a choice of branch. So how are you sure that this branch corresponds to the original integral?
Because yeah, we will actually precisely see. I mean, we can. So let's take this. Of course, for when psi is smaller than 0 and eta is smaller than 0, then of course both have a branch, but in total there is no branch. So for that case this is bigger than 0, so you don't need a phase. But as soon as, for example, eta becomes is positive, then you are at this case, and indeed then you have a branch, which by this phase you might make it single valued again.
Yeah, but I mean you make it single valued by choosing a single branch. I mean there, if I now go around psi, I don't get any 2 pi I s factor.
Yeah.
Exactly. So now it's single valued. And
yeah, but this without justice is not the integral we had here.
Right. And what I'm asking for is why are you sure that this choice of pi and not like instead of 0 and s, like s plus.
I mean, you want to
like 2, if you have 2n
plus 2n,
then
you can do it. I mean, you can do it. I mean, then you just start. You are just in a. You can change the total sheet in which you are working.
Okay.
I mean, we can. I mean, yeah. I mean, maybe it will become clear what that we can. I mean, we can. There's of course still a freedom in at which sheet we start.
Yeah, but that's right. It doesn't affect the result.
It will not affect the result we will see in a moment. So, but you are right. There is a freedom that I could now, for example, add zeta plus 2. I could take or zeta plus 1 even.
Yeah, you could also go around twice and get I pi n s in this case.
I pi n s.
I mean this.
Yeah, of course, yeah.
Yeah, but then in that case, instead it is not true anymore. That's why I was saying that's a choice of branch. I mean, once you fix this phase that way, you're fixing.
Well, I should start at some sheet.
And you're
this
you're fixing the whole thing on that sheet.
I mean, we go now through the cases, and so then we'll see that how it looks like. So we will now look what this phase does, or how we can accommodate it when we go in the complex eta plane. So of course the points where something happens is 0 and 1. No? So a priori here we integrate from here to here, but so we have to make a case by case study. So we will discuss this case. We'll discuss this case. And we will discuss this case. And then we will put things together. So this is the case we have just discussed here. Over here we have eta is smaller than 0 and psi is smaller than 0. So according to this rule, this is positive, so we don't have a phase. So we just we just do what is asked for here. So we just integrate here. So only something will happen once we hit the zero. So what happens? What happens when we hit the zero? Then xi is still smaller than zero, but eta is now bigger than zero. So we will suddenly have this case. So we will pick up a phase according to this factor here. So we will pick up the phase e2 pi is mi pi s. So from going from here to here, we will pick up a phase. So how I can pick up this phase? I can just do this. I can just I can accommodate or get this phase by just moving around here in the complex eta plane. Now, of course, this goes well until I go up to 1. Then up to 1 at 1, something again happens because then this factor does something. So for before I hit 1, this phase according to this rule, both are positive because xi is anyhow negative. So 1 minus xi is positive. So I have in this case I don't have a phase in from the sheet from this sheet from the sheet in determined by u. But then I change this sheet, so I should again get a phase in e2 phi iu. So then I encounter this factor. So this is now, if I would go like that, I can forget about this phase factor because it would automatically be built in by choosing the counters like that. And now we can discuss this case. So that is a case where we have where xi is positive. So we essentially have already a phase, namely the phase in e pi s, because eta is negative and xi is positive. So we have a phase. But then here, then both eta and xi are positive, so we should get rid of the phase. So we will get e to the I minus. And then you can for this case it's the same as here because this doesn't distinguish this case. So we have again get the phase. And then you can, in a similar way, do this case, you will find this. So what we have learned now is that we can very easily accommodate this phase or describe this phase by doing instead of performing this eta integration from minus infinity to plus infinity by going along this orange contours. Are there questions to this? Questions? Okay, so it's clear. Now we have only to put things together. So what we did here, we split this side integral into 3 pieces, and now we see that actually we can deform these counters, and then deform this counter to infinite, so it will not give any contribution. The only guy which contributes is this guy, so we can either choose this count and deform it like that we get a contribution from this, or this must be of course the same contribution, even the same contribution, that the form is counted to the other side. Or we can either take the green or the red. This is all what we get for this complex integral. So let's write down what the what, for example, this violet contribution is. So for this, what we have to integrate, as described here, the eta from minus infinity to 0, and we get one phase from this direction, and then we integrate from here to here, so we get a minus sign when you write it like that, and we get the reverse phase. So this is the p factor coming from these counters. And for the psi, I mean, this is just this part. And then, as I said, by that we have completely taken care about this phase. So I only need to rewrite this integral from here. And the eta, I mean, let me write the, I mean, I can let me write the eta integration. Because now you see already that two open string integrals are emerging, and we only have to understand to what ordering these open string amplitudes correspond to. And of course, this factor is trivial. I mean, this factor gives just a 2i sine pi s. So let's put things together. So this corresponds to an open string integral where C1 is at 0, C2 is at psi, and C3, maybe you should write x1 for the open string, is at 1, and the last one is infinite. Why do I see this? Because I see, for example, that C1 minus C2 is psi, it comes with an exponential s, which is k1 times k2, and 1 minus psi is 2, 3, and 2, 3 is, so it's k2 k3, which is k1 k4, which is u. So this is clearly corresponds to an open string amplitude ordering 1, 2, 3, 4. And actually now all these integers here, I mean, these are just go into this formula here. So you might say, if I wouldn't have started with gluons but with some massive state, then we would get the corresponding massive amplitude here. And here, so what amplitude is this describing? Okay, I have the same. I might take the same fixing. I mean, I do need the same fixing because I have the eta to the s, so the k1, k2, so this must correspond to this case, and the c3 and 1 and before at infinity. However, now I integrate the vertex operator of the second, as a position of the second vertex operator is integrated before the first vertex operator. So I get something like 2, 1, and then 3, 4. Right? and of course the sine factor in the 2I is cancelled by this I over 2. So then we have the result for the violet expression, which is then sine pi s. Okay. Now I can do the same exercise for the green guy, and it has to be the same, of course. So if I do the same exercise for the green guy, no, this is the green. Violet. I get it. Of course, nothing changes for the xi integration. Because the xi integration gives me again this guy here, and since for both cases xi in this region, I mean I get the same open string amplitude from xi, but the other integral will now be 1, 3, 2, 4. And now, I mean, you might say, why is these equations are the same? Now again, this amplitude relations come into the game. I mean, there's an amplitude relation, which first of all, this is nothing else than velocity 1, 3, 4, 2. And so this amplitude and that amplitude are related to each other by the corresponding amplitude relation. So indeed, there's this amplitude relation, which we had derived yesterday, sine pi u and pi s. So by that you can. So this is of course by parity massless, so you don't get minus and 1, 4, 2, 3. And now I have the relation, I mean 1, 2, 1, 3 is sine over u, sine over pi s, which cancels this times this guy. So they're the same, which must be of course is the case. And if you plug in here so for the concrete complex integral, I wrote down the result before the coffee break. Now this is now how we get this. This was a complex integral for the graviton scattering, so we just have to plug in the amplitudes here, so the gamma factors, and by that you can find precisely that. So this is both, of course, lead to the I, which was this complex integral. You just insert the amplitudes and you will find what I have written down. And I do not want to even want to write it down. So this is how this complex integral emerges, or how it can be derived. Are there questions to this? Is it completely clear? So now we also know how the endpoint case works. I mean, the endpoint case is of course just a generalization of this. Of course, it's much more tedious because then you are in multi-complex dimensional plane. But it will give us a generic expression of any complex integral in c to the n. So the endpoint case. Again, we do this fixing, which proved to be very convenient. So in that case, we have to do the following integral. Of course, this kinematic part again can be reduced on left moving side and right moving side to now to a sum over n minus 3 factorial Young-Mills sub-amplitudes on each side. So we don't have to. We now pretty much know what to do with this kinematics. So we can concentrate on the integral. Or the integral to be done in that basis. And we have already seen that any additional integers in this integral will be can be trivially taken into account because they will be not an issue for branch cuts. And now, as before, we can now first of all parameterize each of the n minus 3 complex planes in terms of this parameterization. And we simultaneously deform all y integrations to counters along the imaginary axis that we did before. And then we reduce, as before, this real parameters psi and eta. So the I runs from 2 up to n minus 2. And then, of course, we get a Jacobian, which is now I over 2 n minus 3 for each this is coordinator. And then a priori we get again this psi integrals. Now again we have to, since we have deformed this real integration to the complex imaginary, to the imaginary axis, where we map all these branch points, we have to worry about how to make it single-valued. So again we introduce the phases, which is completely analogous as in the previous case, because the phases of one plane do not affect the other plane, because we have different integers and different coordinates. So we can introduce exactly the same phases. Let's have it here, which now is and then there's a zeta appearing. Zeta I and zeta shown. Okay, so this is completely obvious. But what is important here again as before is that for a given ordering of this psi i's and eta j's, this is just a number. It doesn't depend on the integration. So it's just a number. So that means for any given arrangement of psi and etas, we get just open string amplitudes. Products of two open string amplitudes. So that means the whole problem can be written or boils down to sums over squares of product of open string amplitudes. Now this will boil down the whole integral to I want to write that here. So these are orderings which determine the orderings of the size, which then of course according to all what we did before could give rise to a certain open string sub-amplitude. And then for this given ordering we draw these diagrams in the complex eta planes and see from which we get the contributions, and then we have disentangled, we have disentangled the phase and and we can just interpret the eta pieces as another open string amplitude with a given ordering. And so with the phase here in addition, that would mean we still have the contribution from all eta integration before deforming the counter. So that would mean here it's not yet what we had before, because actually this is a sum over 1 over 2 n minus 1 factorial squared terms, which for n equals 4 is 9 terms. So this is not yet clearly not yet the reduction between the space factors. So why do we have 9 terms? I draw this three diagrams for psi smaller than 0, psi bigger than 1, and psi bigger than 1, and then we have this classification. So eta goes from minus infinity to plus infinity, so this is a complex eta plane. So you get a priori from each eta integration from here to here, from here to here, you get some sub-amplitudes describing this. So you get 3 times 3, you get 9 terms a priori, but only when you analyze the counter with this phasor, you will see that then it boils down to 1 term in the 4-dimensional case. So this is of course some work to do. That what we have seen that after analyzing the counters, that it boils down to n minus 3 square terms. And this gives you precisely, when you do this, which I cannot do in the lecture. So if you do this analysis really in the multi-complex dimensional eta planes, then this formula, this terms boil down to I can also write it like that, because times, okay, let's find it here, S rho. So this is the kernel which we had already met this morning, and these permutations are n minus 3 permutations acting on these indices. So I just write it now, kind of in the morning I just wrote this whole object as S alpha sigma, but now I write it more explicit to see where on which it acts. So similar here. And then this is multiplied with another, again you can write it in terms of a matrix multiplication, 1 rho 2. And the mystery somehow is always that that this comes with n minus 1. No? But recall this was the combination we had also for the disk integral. So this is now the full formula for this integral. So it was an integral in the case that you have here. I didn't specify which closed strings we are scattering. So for example, you can now take clones, and then this would be then open superstring amplitudes and describing two massless clones. And if if you have some massive particles, then you would get here the corresponding, I mean, you split the closed massive string state into two pieces like a massive tensor or something like that. So you see it's precisely the same form as we had for the open superstring amplitude, with this term replaced by this is a full-fledged string amplitude, so of course the supergravity amplitude scattering a gravity from the field theory you just get by taking the field theory limit. Then okay, I made something. This is not yet the kernel. This is some script. This should be script S. Let's write it like that. So these are the sign factors we had. We had also those. This is sign pi s. We had for graviton case. So when you take alpha prime goes to 0, then all the sign factors become are replaced by the arguments. So in particular for the 4-point case, this s script s was sign pi s. So this becomes s. And then these amplitudes become Young-Mills amplitude. So you just put Young-Mills as index here. And then you have the gravity amplitude in field theory. And then, so you have Young-Mills here, you have this, then this becomes just the kernel we had this morning, and then this becomes another Young-Mills amplitude, which if you would replace it by a virtual field integral, then you get the open superstring amplitude. So there's a nice, perfect match between the closed superstring amplitude and the gravity amplitude in field theory and the open superstring amplitude. So they use all the same building blocks. Do you want me to finish? Okay.
They have also the control in a couple of hours, so maybe they want to test it.
Yeah, I'm done now actually for today.
Okay. But just,
I could write down you the explicit form of this kernel, but you can look it up in my papers. Or
about the kernel, is it obvious that it is the same kernel that appeared this morning?
It's
I
a
trust
sign.
you, I mean, that's, yeah.
Yeah.
It is obvious that from
Yes,
these
yes.
double integrals you get precisely the same kernel that you had this morning computed in a different way.
I mean, you have from here you get the explicit form for the kernel.
Sure.
In terms of sign factors,
yeah.
Lots of sign factors, and then if you do this limit, you will reproduce the explicit form we computed this morning from the integral from the.
But these two kernels are computed in two different ways. One
yes,
comes from a
different.
closed string where the integral just
yes,
disentangling, if you like, the
yes,
two complex
completely
integrals.
different. So
yeah,
I should say that this is actually now this is the KLT relation. When you get this name, indeed, I mean when you look at this paper, Kawaile and Hai, they only did it for 4-point and 5-point, and then they were too lazy or didn't know how to write a general formula. They only wrote down this formula, and then because Bernd Dixon really wanted the gravity result, took the result and wrote a general formula for this kernel because they needed it to extract the field theory term, and therefore actually to refer to this kernel one should refer to Bernd Dixon philosophy just for the S. There's an explicit form. You take this explicit form, takes the field theory limit, you will find it's a kernel we have seen in the morning.
Any other question? If not, maybe we can stop and continue tomorrow.
Thank you.